Welcome to the Elliott High Network. I'm your host, Sola Warchow. The Washington Teachers Union has launched a major initiative called Learning Doesn't Stop, Lessons on TV. In the first lesson, Ms. Keo from McKinley Middle School will be discussing gravity. The second lesson will be conducted by Ms. Tyson from Charles Hart Middle School. Take it away, ladies!
Good morning and welcome to our science segment. I'm Ms. Keo from McKinley Middle School. Shout out to my navigator family. And today we are going to talk about gravity. During our lesson today, we're going to investigate and describe the effect of the force of gravity on two interacting objects. And then we are going to take all of that data that we collect to design a parachute later to reduce the motion of an object falling towards the ground that is being affected by gravity. So, you ready to get started? Let's do this. Now, before I get started, I'm going to go ahead and shut off my phone or put it on Do Not Disturb, as should you, so that we're fully engaged. Now, let's go ahead and get ready. Oh man, well that sucks. Don't you hate it when your phone just falls to the ground, or like if you're laying in bed and it just falls on your face? Well, sometimes I wish my phone wouldn't fall so easily, or because I'm short and my secret wish is to be a basketball player and I could never be able to slam dunk because I'm so short, 5 feet tall. Now, I sometimes wish that I could just jump and not fall to the ground. So actually, are we even sure that we fall towards the ground or towards the center of the earth? Let's go ahead and try it. So I'm going to move my cart here real quick. And what I want you to do is get up, get up off the couch, whatever it is, and all you have to do is stand and jump. What happened? Well, I fell to the ground. Let's try it one more time, just in case. Okay, now I'm really going to try hard to jump. Ready? Yeah, didn't really work out so well. And that is all due to something called gravity. Gravity is a force that will pull you towards the ground. Now, I need to know a little bit more about this gravity business. Does it affect everything? Does it affect everything the same? So here's where I want you to do a little bit of an exploration. Grab two objects with relatively different sizes. Now here I have a book, and then I have a pen. Now I'm wondering what would happen if I dropped both of these from a really high height at the same time. What would happen? Ready? 3, 2, 1, go. Wow. I don't know about you, but it seems as though it hit the table at the same time. So what I'm going to try to do is drop it from an even higher height to see what would happen. I got my handy dandy step stool. And then I'm going to pull this table back just so that you could see me. Now, also, if you're doing this at home, please make sure you warn your family so that they're not startled when they hear a loud noise. So, let's go ahead and try to drop this from an even higher height. Ready? 3, 2, 1. Wow, I don't know about you, but to me, it seemed that it hit the table at the same exact time, even though one has a bigger mass than the other. Now, I did some research, and it turns out in the 1600s, a young scholar named Sir Isaac Newton, you may have heard of him, Sir Isaac Newton noticed an apple falling from a tree. Some legends say that it fell on his head. Neither here nor there. Now, he concluded that there is a force pulling the apple towards the center of the earth. A force is a push or a pull. Just like how your parents force you out of bed. They either pull you out of bed or they push you out of bed. But the unique thing about gravity is that gravity is only a pull. Gravity is actually an attractive force between any object with a mass. Now, I have a mass. This textbook has a mass. This pen has a mass. And no matter how hard I try, I don't have superpowers. I can't just try really, really hard to get this pen to come towards me without me going ahead and grabbing it. So why is it that gravity is an attractive force between two masses, but I can't sit there and attract this pen towards me? Turns out my mass is so small and this pen's mass is so small that the attractive force is nearly negligible, which means it's just really, really weak. How we measure gravity is really by large masses. Now, what has a huge, large mass? Well, the Earth. The Earth has such a huge, large mass. And I'm so really, really small, but if I really, really tried hard and I work out to play tug of war with the Earth, I'm gonna lose no matter what. Why? Because I am so small compared to the Earth. And that's why this pen and this book, even though they are different from each other, their masses are so much smaller than the Earth that the rate in which they fall towards the Earth is going to be the same. That's why they hit the table the same. Now that we're armed with the knowledge that gravity is an attractive force between two masses, the largest mass we're dealing with is the Earth, and all objects fall towards the Earth at relatively the same rate. How can we slow it down for, say, skydiving enthusiasts or people jumping out of airplanes? How can we slow down them falling towards the Earth so that they can land safely? Well, a quick and easy answer is by creating some sort of parachute. So if the force of gravity is pulling you down, we need something that's going to pull us up. Now, force of gravity is very strong. Nothing is bigger than the Earth on Earth. But what we can do is we can use something called air resistance. Air resistance is just friction due to the air. Like when you stick your arm out of the window and you can feel it flapping on your arms. So what we're going to do is we're going to build a parachute to help slow down an object like Sir Charles Darwin falling towards the ground. Now, Sir Charles Darwin, he falls. Pretty unsafe for him. Now, I'm going to try to create a parachute for him. And for a science spotlight, if you love seeing how things fly, fall towards the ground, maybe an aerospace engineer is a job for you. Something to consider. So I scrounged around my house and I tried to find some recyclable materials that resembled a parachute. I have some tin foil, some string. You might also need some tape and a pair of scissors. Try not to cut up anything that your parents are going to miss. Otherwise, I can't help you when you get in trouble with that. So, some things to consider if you're designing a parachute. You could consider the shape. You can consider the materials. Do I think tin foil, aluminum foil, is better than a paper bag or a newspaper? So consider those things first. Now, what I'm going to do, I would like to start with aluminum foil, just to see how Sir Charles Darwin will fall. I'm going to take some tape and some string. And remember, you are not limited to using these materials. It's anything that you have laying around your house. So I have some string that I've cut out, and I'm going to make a little parachute for Sir Charles Darwin. Cut up some tape. And I'm going to just use aluminum foil in the shape of a square, just to start out. I'm going to plan my design, make a little parachute. Now, before I test my parachute, what I'm going to do is find a safe height to drop your object. Now, you could use a Lego or something small. It doesn't have to be anything big. I just happen to have this bookmark that I put a little bit of a weight on so he knows to fall down. So I'm going to pick a height, maybe the top of the stairs, or you can step on a step stool and you can drop him. And I can grab a sibling and you can actually time how long it takes for him to fall. Record that. That's what we call our control. So then we can see if our parachute actually is effective in slowing down the motion of an object due to the force of gravity. So now I'm going to test my parachute. I'm going to find some way to attach Sir Charles Darwin to my parachute. And once I do that, I'm going to then test it and time it. 3, 2, 1. Seems like it's a little slower, so I do want it to land safely. So what I would like for you to do is go ahead and try it at home. Test out different designs. What if you use a combination of paper towel or the coveted toilet paper? Don't use that because someone might be mad. Or maybe some magazines or more tinfoil, or maybe you just use a little bit of string. The world is your oyster. Go ahead and try it out. And then when you're done, take a picture, record your data, and use the hashtag KeoScience. And if you want some more resources, you can actually get more information about this lesson, about other careers related to creating parachutes on www.wtulocal6.net. Thank you so much for coming in and joining in this science segment. I'm Miss Keo from McKinley Middle School. Until next time, scientists.
Hi everyone, welcome back. My name's Ms. Hjort-Tyson. I'm an 8th grade math teacher at Charles Hart Middle School. I'm so glad that you guys could join us again for another math lesson, because today we are going to focus on proportional relationships. So just to give you guys a very quick definition about what a proportional relationship is, a proportional relationship is a relationship between two or more equivalent ratios. So now, in order to fully understand our definition, and in order to apply our definition to what's about to come, we need to kind of go back and work on some background knowledge. And that background knowledge revolves around equivalent ratios. So we're going to take a few minutes, explore what an equivalent ratio is, and then we are going to talk about how that connects to determining if something is a proportional relationship or not. So what I'm going to do now is I'm going to show you guys a situation. Here you can see I have 4 squares. I have 1 blue square and 3 red squares. Our goal is I want to write a ratio to represent this situation. Now, to help you guys remember what a ratio is used to compare different quantities in the same situation. So for example, we can use a ratio to compare the number of dogs and the number of kittens at a pet store. Or we could use ratios to compare the amount of chocolate candies versus peanut butter candies inside of a candy jar. We're going to use numbers to represent the relationship between their quantities. So coming back to my example up here, as you can see, I have 4 squares. 1 of them is blue and 3 of them are red. So if I wanted to, I could write a ratio that represents this relationship. And the ratio I would write is that there is 1 blue square to 3 red squares. 1 blue square, 3 red squares. Now, this is one way I can write my ratio. I can write it as a sentence. Or, because mathematicians like to shorten things a little bit, I can write my ratio other ways. I can write it as 1 to 3. I could also write it as 1:3, or I could write it as a fraction as 1/3. But the thing you got to remember, though, is I kept the same pattern when writing my ratio. My blue square always came first, and my red squares always came second. My blue square, my red squares, my blue square, my red squares, my blue squares, my red squares. Now, this is what a ratio is, but what does it mean to be an equivalent ratio? Ratios are equivalent when they're equal. So let's look at an example to see exactly what an equivalent ratio is. So here you see, I have the example we just talked about. And then I wrote the ratio right here, the ratio of my blue squares to my red squares, which we said was 1 to 3. So now I want you to look at this example down here. This time I have 8 squares, 2, 4, 6, and 8. So if I wanted to talk about the ratio of blue squares to red squares, I would say that I had 2 blue squares and 6 red squares. Now, if I wanted to write that as a ratio, and I'm going to use the same format that I did for our first example, I would write that as 2/6. Now, all of you out there that have experience with fractions, you should notice something very important about this fraction. And what you should be noticing is that this fraction can be reduced into a simpler fraction. And the way you reduce a fraction is by dividing the numerator and the denominator by the greatest common factor. So when I look at 2 and 6, I know my greatest common factor is 2. So if I divide 2 by 2, I'm left with 1. And if I divide 6 by 2, I'm left with 3, which means I can reduce 2/6 to 1/3. And as you guys see, my ratio up here was 1/3, and my ratio down here was 1/3. So since these two ratios are equal, I can say they're equivalent ratios. Now, how does this all connect to proportional relationships? When you look at a proportional relationship, you are going to have several sets to look at, and you're going to have to determine if for each set there's a ratio and if all those ratios are equivalent. Now, that's a lot of information to organize. So mathematicians and scientists or whoever else looks at proportional relationships, they like to organize their information. And they like to organize it into tables and graphs. So we're going to start with a table. And as you can see right here, I have a table. And this table has the number of pancakes I can make based on the amount of flour I have. So for example, I can make 2 pancakes with 3 tablespoons of flour. I can make 4 pancakes with 6 tablespoons of flour, and so forth and so forth. Now, in order to determine if this relationship is proportional, I'm going to have to go through and look at every row on my table to determine the ratio. And if all of the ratios are equivalent, then I know it's a proportional relationship. So let's go ahead and get started. For this example, I'm going to make sure that when I write my ratios, I'm going to write them in the format of number of pancakes over the tablespoons of flour. Because remember, we have to write each ratio in the same format to determine if they're equivalent. So let's start with our first row in our table. Our first row says that I can make 2 pancakes with 3 tablespoons of flour. So if I was going to write that as a ratio, this is what it would look like, 2/3. So now let's look at our next row. I have 4 pancakes and 6 tablespoons of flour. So if I write that as a ratio in the same format, I would have 4/6. Now, all of you out there should notice the same thing we saw with our previous example, which is that this fraction can be reduced. And I know it can be reduced because 4 and 6 have the greatest common factor of 2. So if I do 4 divided by 2 and 6 divided by 2, I am left with 2/3. So what do we notice? These ratios are the same, but let's keep going. If I have 6/9, I write my ratio and it comes out to 6/9. But once again, we notice that this can be reduced because 6 and 9 have a greatest common factor of 3. So when I reduce my ratio, I'm left with 2/3 because 6 divided by 3 is 2 and 9 divided by 3 is 3. So now what we see is that the first 3 rows of our table all have equivalent ratios. However, we can't say that this is a proportional relationship yet. In order to say it's proportional, they all have to have an equivalent ratio. And sometimes tables are sneaky and like to throw in a data point that doesn't follow our pattern. So let's keep going. If I do 8/12, my ratio becomes 8/12, which reduced based on a greatest common factor becomes 2/3 because a greatest common factor of 4, 8 divided by 4 is 2, 12 divided by 4 is 3. Our next one, 10 pancakes and 15 tablespoons of flour, when written as a ratio, looks like this. We notice that that also can be reduced because a greatest common factor of 5 leaves me with 2/3. 10 divided by 5 is 2. 15 divided by 5 is 3. And then finally, we have 12 pancakes and 18 tablespoons of flour. And what I notice is that 12/18 can be reduced with a greatest common factor of 6, which leaves me with 2/3. So what we should notice is that for every row in my table, my ratio is 2/3. And because all of my ratios are equivalent or all of my ratios are the same, I can say that this is a proportional relationship. Now, instead of looking at our information in a table, we can also look at our information in a graph. So what I did right here is I created a graph. And in this graph, I put our x-axis as our tablespoons of flour and our y-axis as our our number of pancakes. And then what I did was I plotted my points, and these are the exact same points from the table we just looked at. But what you guys should be able to do to determine this is a proportional relationship is you just need to look at 2 things. The first thing you need to look at is that this is a straight line. A straight line is one sign that this is a proportional relationship. The next sign I have that shows me that this is a proportional relationship is that my straight line travels through our origin. And just a reminder, because we heard it in last week's lesson, our origin is the 0 point on our graph. It's where our x and our y-axis intersect. So when looking at a graph, you know it's a proportional relationship when you have a straight line that travels through your origin. You don't really need to do all the calculations that we just did. It does help to prove your answer, but those are the 2 keys that you need to know it's a proportional relationship. Now, what I'm about to show you is what a graph will look like if it is not a proportional relationship. So as you see, I have two graphs right here. My first one's right here. As you notice, we do have a straight line. However, my straight line does not travel through my origin. Instead, it intercepts at this point right here. So this, I know because it doesn't travel through the origin, is not a proportional relationship. My last graph, which is this one down here, as you can see, it does travel through the origin, but is this a straight line? No, this is not a straight line. It goes up, up, down, up, down, down. So because this is not a straight line, I automatically know it's not a proportional relationship. So in review, proportional relationships occur when you have a series of equivalent ratios. We can use tables and graphs to determine if a relationship is proportional. So keep in mind, when you're coming up with those ratios, you have to make sure you're reducing them via the greatest common factor to see if your ratios truly are equivalent. So I want to thank you guys for joining in today on our quick lesson about proportional relationships. If you have any questions, please feel free to visit the resources found on the Washington Teachers Union page, where you can get more insight onto proportional relationships, as well as the problems you can use this information to complete during our distant learning package.